after the plenary talk this morning. Our first session is a British session, as I've discovered. So we started with the plenary talk from Cambridge. Now, of course, for fairness, we have to go to Oxford. Then we go back to Cambridge, and then afterwards we have a talk from London. I think that's quite a nice theme. I'm sure the organizers thought this well through. So it's my great pleasure to welcome everyone to the session. The first talk this morning in the session will be given by Grigalius Taujanskas, and the title of the talk is Large Data Decay of Yang Mills-Higgs Fields on Minkowski and de Sitter Backgrounds. Welcome to the talk.
Thank you. It's a great pleasure to be speaking to everyone today. So this will be a rather short talk, but I will aim to present a sort of complete argument nonetheless. So let me very quickly tell you what I'm going to talk about. So I'm going to first have a lightning recap of sort of Yang Mills-Higgs theory and associated classical results. I will then go on to talk about Eardley and Moncrief's famous L-infinity estimates for Yang Mills-Higgs fields, which will lead on naturally to a conformal patching construction and global existence on the Einstein cylinder. And at the end, to reap the benefits, I will quickly talk about the asymptotics that these results imply. Okay, so very, very quickly, the Yang Mills-Higgs Lagrangian on a four-dimensional spacetime is given by the following expression, where the various quantities, so the Yang Mills field F is given by the expression there in terms of the Yang Mills potential A. dA phi is the gauge covariant derivative of the Higgs field phi, and lambda is a positive constant. So I should also say that R here is the scalar curvature of G, and I'm using the convention that my spacetime signature is mostly minus. And I'm also using the Penrose conventions for curvature tensor, so there's an extra minus sign there. And if you believe me, I think all the minus signs work out correctly. So the corresponding Euler-Lagrange equations are the following two systems of equations. The one on the left-hand side is the Maxwell equation, the gauge covariant, or rather the Yang-Mills equation. It becomes Maxwell if your gauge group is U1. And the one on the right-hand side is a nonlinear wave equation for the Higgs field phi. So these equations are conformally invariant. Then they don't have to be conformally invariant. If I had chosen different mass for the Higgs field, conformal invariance would break, but because I coupled it conformally under a conformal transformation, if I rescale my fields correctly, as shown here. So one thing to notice here is that the Higgs field scales slightly differently to the Yang-Mills potential and field. These fields then satisfy the rescaled equations, which look exactly the same as the physical equations, where all the Hatters quantities refer to rescaled quantities on the conformally rescaled manifold. So these equations are hyperbolic. As I already mentioned, the one for the Higgs field phi is already a nonlinear wave equation. The one on the left is also a hyperbolic equation, and one way to see that is to rewrite it in terms of the Yang-Mills potential, in which case it becomes a nonlinear wave equation for A. So they're hyperbolic, and a natural first question to ask about hyperbolic equations is, well, are they well posed? A slightly more interesting question is, perhaps a more precise question is, well, how regular must my initial data be for this well-posedness? And on Minkowski space, we have a famous result by Eardley and Moncrief from 1982, which states that if I take initial data for the Yang-Mills potential and the Higgs field phi to be in H2 cross H1, then there exists a global unique solution on Minkowski space in the temporal gauge. So the work I'm referring to here is the second in a series of two papers by Eardley and Moncrief, in the first of which they prove the existence of a local solution by an iteration procedure, and in the second they extend the local solution by these L-infinity estimates that I will come on to shortly. So H2 cross H1 initial data is good, but in fact, we can do a bit better than that. And in 1995, Kleinen and McAdam proved a celebrated result, which showed that if your initial data is merely finite energy for the Yang Mills-Higgs equations, then there exists a global unique solution on Minkowski space in the Coulomb gauge. So the gauge here is slightly different. That's because Klein and McAdam were only, were first able to see the null structure in the nonlinearities of these equations only in the Coulomb gauge, although this has since been extended to a few other gauges. In 2002, Tau showed that in fact you can do even better than that and reduce the regularity to HS cross HS minus 1, where S is only allowed to be, only required to be greater than 3/4, although here there is no global statement about the solution, only a local solution exists.
Grigalius question?
Yes.
So the H1, the threshold is the energy space, right? Which is kind of very natural. How does this 3/4 come about? Can you comment on this?
So this comes, I haven't actually read the paper in detail, but this comes from these XSB estimates that Tau does and space-time Strickhardt estimates.
So there is no obvious intuition for this?
Not that I know of.
And there is no statement that this is sharp or something like that?
No, so I will say a little bit about that in a second.
Thanks.
Okay, so 3/4 is good. You have local well-posedness, and so as Pepper mentions here, sort of H1 is a natural energy, and you might think, well, are we sort of doomed to local well-posedness if we go below S equals 1? Well, in fact, it turns out no. And in 2009, Kilroy and Tau proved that at least for the Maxwell-Klein-Gordon equations, you have global well-posedness, where S is only required to be greater than √3/2, but it can be less than 1. So there's various interesting things going on here with the minimum regularity of these equations. Okay, so why should one be interested in in lowering the regularity of the well-posedness results of these equations? Well, I claim that this is a physical significance. One is that the finite energy setting S equals 1 is sort of natural from a geometric conformal scattering perspective. But from a quantum field theory point of view, we would probably like to go down to S equals 1/2, which comes from a positive negative frequency splitting argument. And so this is conjectured to be very difficult. If I'm not wrong, S equals 1/2 is the critical case there. So I don't think there are any results about that yet. And what is more, we would like to do that on curved space as well, if we would like to study scattering on curved spacetimes. So alas, there are not that many results on curved spacetimes about this, although there are some notable exceptions. So these are a theorem by Choquet-Bruhat and Christodoulou, which was published at the same time as Eardley and Moncrief's results that I mentioned earlier. And these show that the Yang Mills-Higgs equations are locally well posed on the Einstein cylinder for data lying in H2 cross H1. And another notable result is a result by Crochet and Chatter, which says that for pure Yang-Mills equations, the initial data, if you have initial data for the potential in H3 cross H2, then you have a global solution in the temporal gauge. So this argument is somehow a reproduction of Eardley and Moncrief's infty estimates on curved space. And there are various difficulties that are introduced in curved spacetime. As you can see, there is a loss of one derivative occurring in curved spacetimes that I'll say a bit about in a second. Okay, so how do these L-infinity estimates, at least on flat space, work? So if one goes away and differentiates the Yang-Mills-Higgs equations on flat space, one is able to derive wave equations for the gauge, for the physically relevant fields F and d phi. So I should say that Yang Mills-Higgs is a gauge theory, so there's a redundancy, especially in the Yang Mills potential, but the fields F and d phi are somehow regarded as physical. So why are these equations useful? You might say, well, we already had wave equations for phi and A. Well, the reason for that is that is exactly this gauge redundancy. And if we work with F and d phi, then we're able to circumvent that, as I'll describe in a second. So at least on Minkowski space, having these wave equations for F and d phi allows us to express the solution as an integral over the backwards light cone from an arbitrary point. So this is what that integral looks like, and the coloring here is sort of related to the different techniques that I needed to estimate this integral. And the thing that I will mention here is that the blue terms are the most difficult, and the blue terms are the ones that require treatment using something the Cronstrom gauge. And then that's the point where having F and d phi as your fields really becomes important, because you can make the L-infinity norms of those guys gauge invariant. Okay, so Eardley and Moncrief then go on to estimate this integral expression for F and similarly for d phi to derive these Gromwall type estimates for the L-infinity norms for F and d phi, where the coefficients here are polynomials in time, depending on the H2 cross H1 norm of the initial data. One thing that I want to point out here is that there is a factor of the energy appearing here, and that will, so that means that in particular that the energy should be finite for this estimate to be useful. So, okay, it is fairly easy to see that from now, the L-infinity norms of F and d phi do not blow up in finite time by applying a simple Gromwall inequality. And then it's a simple energy estimate to deduce that. In fact, the H2 cross H1 norm of the local solution does not blow up in finite time. And that's because you can take out the L-infinity norms in front of your estimate, and you've controlled them. So you control the H2 cross H1 norm. And so you've extended your solution to a global solution. So can we do these on curved space? Well, as already mentioned, the Cauchy-Chatin method loses one derivative due to this term that I had underlined earlier. And well, perhaps I don't want to get into the business of doing this on generic curved spacetimes. So let me just think about the conformally invariant, the conformally flat case of the Einstein cylinder, and see if I can use the conformal invariance of the Yang Mills-Higgs equations. And it turns out that what we can do is localize the L-infinity estimates on flat space and then conformally transport them to the Einstein cylinder. So as I mentioned, there is this factor of the energy in the L-infinity estimates by Eardley and Moncrief. And if we were to localize those, we would somehow have to come up with a notion of a local energy. And it turns out that the correct notion of the local energy is simply the local energy in the light cone that you're doing the estimate over. So you take the supremum of the slices, of the space-like slices of your light cone. And equipped with this definition, it's then essentially a trivial matter to retrace Eardley and Moncrief's estimates to deduce essentially the same kind of estimate, but now the L-infinity norms are confined to a local light cone that from a point that I have chosen arbitrarily in Minkowski space. So this is natural to expect, of course, from domain of dependence arguments and the hyperbolicity of the Yang Mills-Higgs equations. Okay, so because my point is arbitrary, of course, then this shows that for locally H2 cross H1 data for the Yang Mills-Higgs equations on Minkowski space, my F and d phi fields are locally L-infinity, at least in the domain of existence of my solution. So what am I going to do with this? Well, so this is where this conformal patching construction comes in. So let me take a small ball of radius r around the origin of Minkowski space, think about its domain of dependence, and let me glue this domain of dependence onto the Einstein cylinder by conformally embedding Minkowski space into the Einstein cylinder. So we end up with the following picture here. So this shaded region is Minkowski space for t greater than 0, and the cylinder is the Einstein cylinder R cross S3, and I've suppressed one spatial dimension here. So I've glued this conical patch k hat onto the Einstein cylinder from Minkowski space. And the key point now is that, of course, in this small conical patch around the origin, the conformal factor that under the embedding of Minkowski into the Einstein cylinder is now essentially equivalent to a non-zero constant. And it then follows after some fairly trivial calculations that the L-infinity norms being finite on Minkowski space locally implies the L-infinity norms being finite on the Einstein cylinder in the corresponding conformally transported cone. And we can perform this construction with this small cone positioned anywhere around the cylinder and patch those estimates together. And altogether, what do we end up with? One can see that you can start with H2 cross H1 initial data on the Einstein cylinder, take such a small conical patch on the Einstein cylinder, map it back to Minkowski space, deduce that you have local H2 cross H1 data on Minkowski space, use the localized L-infinity estimates, and map those back to the Einstein cylinder to deduce that you have L-infinity bounds on F and d phi on the cylinder. So if you patch a number of these around the cylinder, as already mentioned, you end up with these L-infinity estimates on a slab of the Einstein cylinder, where the height of that slab is independent of the size of the initial data, and really only depends on the number of these patches that we choose to patch together. Okay, so from there on, then it's a similar and fairly simple argument to do some energy estimates and deduce that, in fact, your local solution on the Einstein cylinder, which was guaranteed by Choquet-Bruhat and Christodoulou, is in fact global and lives on forever for data in H2 cross H1. Okay, so that's nice and good as a result in itself, but remembering the fact that the de Sitter space and Minkowski space are both conformal to the Einstein cylinder, we can quickly reap some benefits of this. And so here's an expression for the conformal embedding of de Sitter space into the Einstein cylinder. Alpha here is my my time coordinate in the global coordinates for de Sitter space. So taking the regularity of the solution on the Einstein cylinder, I can embed using this overlap embedding H2 into C0.5 the solution that I have into the space of continuous functions on R cross S3 to deduce that my solution is in fact continuous on null infinity on de Sitter space. So de Sitter space is a space-like hypersurface sitting at a finite conformal time on the Einstein cylinder. And because my solution is then continuous, it is uniformly bounded on Scri. And the only thing that then plays a part in estimating the physical solution is this conformal factor, which appears in front of the rescale solution and introduces an exponential, a factor of exponential decay. And I can do a very similar thing for the Yang Mills potential, except here I have to have a sort of space-time metric with a reverse sign in the space-like part. Okay, so maybe this relates back to the question that was asked in the previous talk: why is there exponential decay in the case of lambda greater than 0? I can do a very similar construction on Minkowski space, except here I have to introduce a null tetrad to ensure that we treat the null directions appropriately. And here it turns out that the scalar field decays like u to the -1, v to the -1, and the Yang Mills potential decays. There's a few components of the Yang Mills potential, and they decay along these null directions polynomially, as shown there. Okay, so the final comment is that, of course, because I've used the conformal method here, is that the conformal transport ensures that I cannot have any magnetic charge at infinity for my solution on Minkowski space. However, this is sort of the lowest regularity one can expect to be able to talk about pointwise decay estimates for these solutions. If you had H1, then you no longer are able to talk about pointwise decay estimates because you don't have a Sobolev embedding into a space of continuous functions. Okay, so I think I've almost run out of time, so let me stop there. Thank you.
So thanks a lot for the very nice talk. You finished exactly on time. Nevertheless, I think we can quickly ask if there are some urgent questions for Grigalius. Yeah, Piotr Bison. Piotr, no, sorry. No, sorry, you have to again. Sorry, I wanted to unmute you, but then you pressed again, so now you have to unmute you again. Yes.
Okay. Sorry. I have a remark and a question. A remark is that in physics by Higgs field, you mean a scalar field which is not vanishing at the vacuum, which is not the case. So I would rather call it Yang Mills scalar field rather than Yang Mills-Higgs. My question is, if you change the sign of the quartic term in the scalar field, you will have a focusing scalar nonlinearity. And in this case, without Yang-Mills, it is known that there are very peculiar global solutions which decay very slowly. And I wonder if inclusion of Yang-Mills would change this or not.
Sorry, do you mean would I be able to do the same thing if I changed the sign of the constant in front of the quartic term?
Yes.
So yeah, so the answer to that is no, because the positivity of various energies then fails. So that's why I have to focus on the lambda greater than 0. As you say, if you reverse the sign, then you have a focusing equation, and you not only can have very slowly decaying solutions, but I believe you can have solutions that blow up in finite time.
Yeah, sure. Yeah, but you also have solutions which are global and decay much more slowly than the ones you have. Okay.
Yeah. Yeah, and so just to come back to your comment about the Higgs field, this is a lot of people prefer to call it the scalar field, or Eardley and Moncrief call it the Higgs field, but yeah, because it's massless, it's probably most correctly is called the scalar field.
Okay.
If I may just ask a question, okay. I don't know how to raise my hand, so I'm just going to do this. When you're doing this conformal transformation in your I0, there is a singularity in the conformal factor. Because there are constraints in the equations, one needs to somehow do something about it. So did you look at that? Do you know anything about it?
Well, so part of the point of this construction is that it's all local, and we don't need to worry about I0 because we can always rotate our Minkowski space around the Einstein cylinder to ensure that I0 is somewhere else, and the data at I0 of this patch is taken care of by another patch. So the thing that is a consequence of that is that in fact, you're dealing with solutions here which on Minkowski space have infinite conserved energy. And on the other side, if you start with solutions on Minkowski space, then to be able to transport them to the cylinder, you're forcing this strong decay at I0.
But surely, if you have a singularity at one point, then you're going to no matter how you rotate your stuff, it'd still be there. So I don't see how you can shift the singularity by moving things around.
So the singularity is there. It's just that it doesn't affect the solution in my very small patch.
Right, away from the domain of the influence of I0. But if you want to do things globally. Maybe I'm confused about the setup.
Yeah, I ran through it quite quickly, but maybe we can
Okay.
talk about it.
Good, thanks.
Okay, so thanks a lot for the talk. We switch to the next speaker. Zoe, can you share